It is my great pleasure to introduce Dr. Wooyoung Jang, who is a member of our neutrino group. He was just hired earlier this year through the fierce competition. He's got his PhD from South Korean institution, Gyeongbok National University, which is a very well-known university in terms of its academic ranking. But more importantly, it is very well-known and leader in high energy physics and high energy particle physics, and that university is very well known for that. He did his PhD this year. He completed earlier this year, and at about the time that he was come to the U.S. To join us, this COVID thing happened, so he was in a limbo for a while. In any case, he's now back in the U.S., and it's my great pleasure to have him to tell you about the research he has done at the AMS experiment, which stands for Alpha Magnetic Spectrometer, led by a Nobel laureate, Sam Ting of MIT. And then, he's doing, Dr. Jang is also leading the effort in the search for low mass dark matter at Dune Experiment and other neutrino experiments. Without further ado, I give you Dr. Wooyoung Jang. Go ahead, Dr. Jang. Hello? 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 Did you hear me?
Dr. Jang, can you start now?
It looks like it's frozen.
Yes, now better. Hi, Dr. Jang, please start. Yes.
I was just disconnected. Can I start now?
Yes, please, yeah.
Okay, thank you very much. Good afternoon, everyone. Thanks for introducing me, Dr. Yu. My name is Wooyoung Jang. I'm from South Korea, and I officially joined to the UTA this semester as a postdoctoral research fellow. So I'm glad to be here with you, and I'd like to thank to the UTA Physics Department faculty members for inviting me to this colloquium. So today I will talk about some pieces of my studies that I did in my PhD course. Plus, I would like to present the works I will do as a member of the UTA. So mainly the whole story is related to the search of dark matter. So this is an overview of this talk. There will be 3 different parts in this talk. The first one is about introducing what dark matter is, and the second one is about dark matter search in AMS experiment. And the final section is about the light dark matter search, which I'm studying right now. So let's hit the road by talking about what is dark matter. So in modern physics, dark matter is some exotic form of matter consists of the universe. So if you look at the 2018 Planck experiment, their observation result, it has been known that dark matter consists of 26.8% of the matters in our universe. So in 1970s, an American astronomer, Vera Rubin, published her observation result about the galaxy rotation curve, and it was confirmed as the first persuasive observation supporting the dark matter theory. So let's talk about how she measured this galaxy rotation curve. So every star in a galaxy is a bunch of hydrogen gas. And since the scientists in the Earth knows quantum mechanics very well, one can compare the emission lines of the hydrogen atom at rest to the emission line from one of the stars in a galaxy. So there are 2 different emission lines that astronomers usually use. So one is the H alpha line, which is a visible spectral line in the Balmer series with a wavelength of 656.28 nanometer. The other one is the 21 centimeter line called H1 line, comes from the hydrogen atom. If we look at some stars moving away from us, because of the Doppler effect of the light, we will see a red-shifted hydrogen emission line. And if we aim at the stars moving toward us, then we see a blue-shifted hydrogen emission line. So in principle, by looking at the amount of those red shift or blue shift, we can measure the orbital speed of the stars in a galaxy. So therefore, by looking at stars at a different distance from the galactic center, we can construct a speed versus distance graph, and we call this galaxy rotation curve. By the way, this galaxy rotation curve is predictable by Newtonian mechanics, classical mechanics, especially Kepler's law together with the observation result of the integrated luminosity of the galaxy. Since the brighter stars in main sequence usually have more mass shift, therefore we can estimate the mass of a star by measuring its luminosity. So if we know the luminosity of a galaxy, then the total luminosity of a galaxy, then we know the mass of the galaxy. So and then we can use it to calculate the orbital velocity of some section of the galaxy. Here, in this graph, here the galaxy gray dashed line is the galaxy rotation curve from the Keplerian prediction, and we found that there is a significant gap between this observation and the Keplerian prediction. This means there must be some extra matters that gives additional force to the stars in a galaxy. So scientists named this unknown matter as dark matter. So nowadays, the existence of dark matter has been accepted throughout the scientific communities. There are lots of evidence in the astronomical observations that support this. For example, if you see this figure in the background, I'm sorry, this was supposed to be animated, but yeah, I transformed it to the PDF, then I lost this animation feature. But anyway, so for example, this is a picture of the bullet cluster. The red layer on this picture shows X-ray emission from stars, and the blue layer is a mass distribution estimated from the gravitational lensing effect. So this difference between red and blue layers directly indicates a critical defect of our physical knowledge. And if I say this something differently from a viewpoint of a particle physicist, one can say that we are looking at the conflict between our theory of gravity and the standard model. So currently we know only little about the nature of dark matter. First of all, dark matter must be cold in terms of statistical physics, which means dark matter must be non-relativistic. And to explain the Rayleigh abundance, it must be very stable. Also, the dark matter must be dark, which means it does not interact with ordinary matters by electromagnetic interaction. So as I mentioned in the previous slides, the existence of dark matter is generally accepted by the scientific community based on the huge amount of accumulated observation results. But by now, no one ever observed its particle nature. So naturally, finding any clue of the particle nature of dark matter become one of the most important subjects of the particle physics. However, there are no particles in the standard model meeting such requirements. So therefore, this naturally leads us to the world of the beyond standard model. And this is a Venn diagram of theories of dark matter, which was drawn by Dr. Tim Tite in 2013. In this diagram, 19 different and independent theories are here. So in this situation, we needed some guidance to find out some exit from this mess. So some theoretical physicists in the 1970s have already suggested a category of dark matter which seems most plausible, and this is called weakly interacting massive particle. And this WIMP concept had a special reason to become popular because people found a guideline of dark matter mass in our own scientific framework. The major constraint of it comes from the observation result of the cosmic microwave background, especially the relative density of dark matter that I already mentioned about the 26.8%. And this guideline tells us the mass of dark matter must be in a weak scale. Approximately, this ranges from 1 GeV to 10,000 GeV. People called this sequence of reasonings as a WIMP miracle. The plot on the right shows you the dark matter relative density as a function of dark matter mass divided by the temperature of the universe. And if you look at the center of the plot carefully, you may find the black solid horizontal line. And this line indicates the observed relative dark matter density by the Planck experiment, which is 0.268, 26.8%. To obtain this specific relative density, it shows dark matter must have a certain cross-section. And from this cross-section, people obtain the reasonable mass range of WIMP with most plausible scenario. So how to detect this dark matter? So since I told you that dark matter must be cold, which means they are moving slowly. However, due to the orbital motion of the solar system, we are sailing through the dark matter wind. So when this dark matter comes into our detector system, although they have an extremely small probability to interact with ordinary matter, we can expect they leave some signature. For instance, if we may watch some scattering of particles inside the detector if we build the detector big enough. This strategy is called the direct detection method. In the top left Feynman diagram, if you read this diagram from left to right, you are looking at the Feynman diagram for the direct detection method. Also, there are two more complementary ways to investigate dark matter. If we collide some particles energetically enough, then there is a chance to produce dark matter. And since the dark matter is dark, they are almost invisible by any detectors. And by tracing down any missing energies in the collider event, there will be a smoking gun of the dark matter. So if you read the Feynman diagram from the bottom to top, that is about this method. So the other method is the indirect detection. Many WIMP theories assumes annihilation of dark matter, and they say if two dark matter particles annihilated, and then we expect they produce particle and antiparticle pair. This dark matter annihilation possibly creates some extra electron and positron pair in galaxy. And since the weak scale dark matter collision cannot produce energetic enough particles that can be freed from the galactic magnetic field, they must be bounded in a galaxy. So for your information, it is known that from the ultra-high energy cosmic ray experiment that those extra galactic scale cosmic rays must have an exi electron volt energy scale, which is 10 to the 19 electron volt. But anyway, in our case, they do not exceed those big energy. So such particles produced by dark matter annihilation may wander around the galaxy, and by chance, some of them may arrive at the Earth. Also, we know the fact that collision of cosmic rays with interstellar medium will produce additional positrons and antiprotons. By the effort of the astroparticle physicists, we know this very precisely. So therefore, if we can think about that the excess of any positron or antiproton, such antimatters, there can be a smoking gun of a dark matter annihilation. And this can be measured by the alpha magnetic spectrometer. This device inside the red box is the AMS-02 detector, and it is installed in the 2011 on the International Space Station. And some old members of AMS collaboration said that AMS was just a short name for the antimatter spectrometer, but because of detecting antiparticles in space was the most important job, has to be done by this detector. But now it changed to the ALPA magnetic spectrometer, and this ALPA means the code name of the International Space Station. So the AMS means a magnetic spectrometer installed on the ISS. And Professor Samuel Ting is the principal investigator of this project, and he founded the collaboration in 1995. So I would like to introduce you the AMS detector. So the AMS detector consists of 6 different major parts. One of them is the permanent magnet and the other 5 are the sub-detectors of it. And from top to the bottom, at the upstream side, there is a transition radiation detector here, and we call it TRD. This identifies positron and electrons from the tremendous amount of proton background. And we have the time of flight that provides speed of the particle and electric charge of it. And those pink layers in the middle of the detector, these are the silicon tracker. A silicon tracker measures the electric charge of the particle and its momentum. And then below of the lower time of flight, we have the ring image Cherenkov detector, which provides speed and charge of the particle. And beneath of it, finally, we have the electromagnetic calorimeter, which measures the energy of the electron and positron. So this is about the magnet. In the AMS detector, a system of permanent magnets is used. It is basically a neodymium magnet. And using 6,000 of tiny magnet blocks, we stack them in a specific orientation, like the figure on the left here. And then we can get some uniform magnetic field with a 1.5 kilogauss intensity. This plot in the center of the slide shows you the field intensity profile of some piece of the AMS magnet. And to help to get some instinct about this magnetic field, for example, if we fire a 1 gigaelectron volt proton into this magnetic field, then it will give approximately 0.7 centimeter deflection. So then let's move on to the transition radiation detector. The transition radiation detector is located at the top of the AMS detector. And by using a phenomenon called transition radiation, TRD distinguishes electrons and positrons from large amount of proton backgrounds. For example, consider we have 2 different dielectric materials here. Let's say the epsilon 1 and the epsilon 2 are their dielectric constants. And consider a charged particle travels through this dielectric boundary. Then the particle will feel some stress because there will be transitions of electrons' energy state while it travels across the boundary. If the speed of incident particle is fast enough, it will have larger Lorentz factor, and it will have much bigger effect of length contraction. And in terms of the special relativity, and therefore the particle feels more rapid and violent energy state transition, and this produces transition radiation photons. For example, let's say we have proton and positron with same momentum. Since the proton is more massive than positron, the Lorentz gamma factor of positron will be much bigger. And compared to the proton, those positrons will produce more TR photons. Therefore, we can distinguish positrons from protons. So, in order to maximize the production efficiency of TR photon, the transition radiation detector has a radiation fleece. Since those in the center of bottom, there's a picture from an electron microscope of the radiator fleece. Since those fibers are randomly distributed, it makes lots of dielectric boundaries and enhance the chance to produce TR photons. And below this radiator, there are gas proportional tube as a lead out. These tubes are filled with 80% of xenon and 20% of carbon dioxide gas mixture. And this gas will be ionized by charged particles and the TR photon. And there are cathodes at the center of the gas tube, and anode covers the cathodes. And there's a high voltage is applied here to collect those currents by ionized electrons. And if you can see the plot on the right bottom, because of the additional TR photon effect, positrons always deposit a larger amount of energy compared to the proton. And the next is silicon tracker. In AMS detector, there are 6 planes of silicon trackers, which are made by 9 layers of double-sided silicon microstrip sensors. Once a charged particle passes through this silicon tracker, electron and hole pairs are created, and these current collected by electric field applied for each sensors, and we read this signal by amplifying it. And the silicon tracker provides approximately 10 micrometer coordinate resolution in the x direction, which is the bending direction by the magnet. Also, the tracker provides charge measurement, since the energy deposition of charged particle in this material is in a certain material is proportional to the square of its charge. And using this beta formula, we can reconstruct particles charge using the energy deposition and the track reconstruction. So here the energy deposition is given by the deposit energy dE information, and track gives the dx information. So for example, this plot on the right bottom shows the energy deposition of a helium sample as a function of kinetic energy per nucleon. And the cyan dotted line is the beta formula in terms of the kinetic energy per nucleon. And the next is the time of flight. The time of flight provides the main trigger of the experiment, called the level 1 trigger in the AMS experiment. Time of flight system is composed by 4 planes of plastic scintillation counters, and 2 for upper time of flight, and the other 2 for the lower time of flight. The PVT plastic is used as a scintillation material to provide a high-speed trigger, and it gives about approximately 150 picosecond of timing resolution. So using these timing differences recorded by upper and lower time of flight reconstructs particles timing information. First, we look for the track reconstruction to know the actual travel length of the particle, and dividing this by time difference, it gives the beta measurement. Also, time of flight gives redundant dE over dx information, so we have another way to reconstruct particle charge. So in the bottom of the lower time of flight here, we have a ring image Cherenkov detector. We call it a REACH. REACH uses a Cherenkov effect to obtain signals, and I'd like to explain this briefly. When a charged particle passes through a dielectric medium, the incident charged particle polarizes the nearby molecules, and during the relaxation process of this polarization, electromagnetic radiation can be produced. Usually, but if the phase velocity of the particle is slower than the velocity of light in that matter, then those radiations are not coherently emitted, and therefore they are easily dissipated. But if the phase velocity of the particle is faster than the speed of the light in that specific matter, then the radiation emits coherently and constructively in a specific direction, and it makes some cone-like shape. The opening angle of this cone can be written in terms of the particle speed beta and the reflection index of the dielectric material, and here. So on the top of the actual AMS ridge, we have two different types of ridge radiator. One is aerogel, and the other is a sodium fluoride here. This sodium fluoride works both as a radiator for ridge and as a window to the electromagnetic calorimeter, which is located below the ridge detector. And the sodium fluoride is selected to minimize the material budget in the path of the particle before it reaches to the ECOL. And on the bottom of this ridge detector, there is a array of photomultiplier tubes to record the Cherenkov radiations. So once the Cherenkov radiation is emitted from the radiator, those photons are absorbed by the PMT array, and we reconstruct ring shape of this Cherenkov light. And using the track information together, we can calculate the opening angle of the radiation, and then this gives us the particle speed. Also, if the particle carries more electric charge, then it will make stronger polarization in the radiator. Therefore, it produces more intense Cherenkov light. And then from this intensity of Cherenkov light, we can reconstruct the particle's charge too. So we have another redundant charge measurement from the ridge. And finally, we have an electromagnetic calorimeter. The AMS ECOL has a lead and 5 plastic fiber sandwiched structure, and there are 9 layers of them, which are stacked alternatively parallel to the X and Y axis in order to reconstruct the 3D shower shape. And the AMS ECOL provides energy resolution in the scale of 10.4% of a stochastic term. So those different subdetectors are consisting the AMS02 detector, and there are total 300,000 channels, and the whole detector system produces averages 3.7 megabit data per each of the event. So I'm going to move to the data analysis part. So if you want to select some golden events to look for the positron excess, we require clean events first. So we can require single event. We require a single track in a single event and single beta measurement. And also by requiring only the positive time difference in the time of flight, we can select downgoing particles. And the single TRD track will give us the clear separation of positrons from proton backgrounds. And finally, single electromagnetic calorimeter shower requirement will promise us the accurate energy reconstruction. So among those clean events, now we want to separate the proton background from our signals. So our signal is electron and positron, because almost over 90% of cosmic rays are composed by proton. Strong identification capability of proton background is very important in this measurement. First of all, we collect some energy deposition of the electron and proton on the TRD from the test beam data. We'll have a maximum 20 energy depositions for each event, because we have 20 different TRD layers. And then we normalize the energy deposition distributions to obtain some probability density functions. And after then, we calculate the electron likelihood and proton likelihood using this definition here. So since we have 20 different TRD layers, ideally, there will be 20 different probabilities here. Let's say an unknown particle deposited approximately 18 kilo electron volt energy here. Then the probability that this is occurred by electron is given as red arrow here, this probability. And the probability that this is made by proton is given as the blue arrow here. And we defined the electron likelihood and the proton likelihood by the geometric mean of each probabilities under the different hypotheses. And finally, using those electron and proton likelihoods, we calculate the value called the log likelihood ratio here. This is called the TRD likelihood or TRD estimator. And if we collect some electron sample, this value will show some this lead distribution. And if we collect some proton sample, then this TRD TRD estimator will distribute like this blue distribution here. So in the actual data, this is an example of in the near the 1 GeV energy bin. The actual distribution looks like this. And since we need to count electron and positron separately, plot on the left is made by positively charged particles, and the plot on the right is made by the negatively charged particle. We can separate them by using the track curvature sign using our tracker and magnet. So using the Monte Carlo distribution of this positron and proton and electron as a template, we can extract the number of positrons here and the number of electrons here out of this proton background. So if we do this for each of energy bin, we can obtain a plot like this. I copied this plot from the Professor Ting's slide. When I did this study, at that time we had much smaller statistics, so our analysis was limited to the 350 MeV region here around here. But this one is presented in the 2018, and it extended to the 800 gigaelectron volt. Here the red bullets are the AMS experiment in 2018, and the red solid line is a theoretical estimation of positron fraction with 1.2 tera-electron volt dark matter assumption. And the green line is the theoretical estimation of no dark matter scenario. And it appears the data and theories shows a good agreement, and they actually are. However, there are some problems here. Some astrophysicists raised an issue that this kind of behavior can be explained not only by dark matter, but also some astronomical object. And this astronomical object is pulsars. And pulsars are highly dense and rapidly spinning astronomical objects. And they can produce a very strong swirl of magnetic field around themselves. So, and then if by chance energetic photon can travel nearby this pulsar, then this photon can produce additional electrons and positrons pair around it. Currently, the AMS result of both positron fraction and this positron flux alone cannot rule out this pulsar model. But the AMS collaboration is hoping to do this by coming this 2024. And interestingly, the AMS collaboration released their anti-proton to proton ratio result, which cannot be explained by the pulsar model. This gives some optimistic future to the AMS collaboration. But anyway, however, although there are big effort for this indirect detection matter, declaring the discovery of dark matter is not an easy thing. In order to convince all the scientific community, scientists always require some kind of a complementary experiments. So in our case here, we need to see some smoking gun from direct detection or accelerator-driven measurement. This sensitivity plot shows you the status of the WIMP search rays in the direct detection method community. And we don't have any definitive clue of dark matter from them right now. And we are running out of phase space here now. This is a kind of limitation of the indirect measurement. But if we think differently, there is another way to search for dark matter. So if we go back to the earlier part of this talk, I mentioned that the WIMP miracle is the reason why the WIMP hypothesis is favored by most of physicists. This was about the dark matter mass must be in the weak mass scale, which is from 2 GeV to 10,000 GeV. Here, the lower limit is proposed by Lee-Weinberg theory, which is purely based on the standard model. So the suggestion of our new light-dark matter theory is, why don't we introduce a new interaction? I know that this is very bold assumption, but this solves a lot of problems related to the dark matter at once. So including the relic density problem and the weakness of dark matter interactions, and also the Lee-Weinberg limit problem. Therefore, we can explore the sub-GeV mass region for dark matter search, and we call this type of new interaction as a polar interaction. Let me explain why this is called the polar interaction. In this model, new vector boson A prime is introduced, and we assume that this new boson can be coupled with standard model particles, and then we expect the neutral meson decay process can produce such dark matter pair. Since this standard model particle and dark matter interaction always requires some new force carrier boson A prime, we call this interaction a polar interaction. Sometimes we call this boson A prime as a dark proton. So now we can think about where can we find this type of dark matter most frequently. The answer is the neutrino experiment. Typically, the neutrino beams are made by collision of proton and certain target material, and this fixed target interaction produces a lot of charged mesons, and the decay of those charged mesons will produce lots of neutrinos. In order to increase the neutrino flux, neutrino experiment typically requires high intensity proton beams. For example, this is a layout of the Dune experiment, especially the near detector site. From the right of the figure, 120 GeV high intensity proton beam comes out from the main injector, and this proton beam smashed into the 1.5 meter long cylindrical graphite target structure in the target hole complex. And here a lot of mesons are expected to be produced, including the neutral pions. Now, while these neutral pions travel through the decay pipe, most of pi 0 will decay into 2 photons. And we are expecting these dark matter pairs will be produced here among those decay of pi zeros by the polar interaction. And we will detect those dark matters using the Dune near detector here. So, in our model of the light dark matter, the dark matter interacts with standard model particle by exchanging the dark photon. What we are expecting inside the dark matter is scattering of electrons or nuclei by dark matter. And the neutrino experiment, like the Dune, is equipped with a very high technology precision detector called the time projection chamber. And especially in many cases, to produce more frequent neutrino and nucleus scattering, we use liquefied argon as its medium. So we call them liquid argon TPC. So I think many of us already know about the time projection chamber because Professor David Nygren of the UTA is the inventor of this technology. When I took a course of particle detector in Korea, I thought this idea is a revival of traditional bubble chamber with the modern digital technologies. And the working principle of the time projection chamber is unbelievably simple, but its outcome is really powerful. We have anode and cathode at the size of the liquid argon volume, and we apply uniform and stable electric field across the detector volume. Actually, to obtain this uniform and stable electric field, we need a detector component called field cage. The UTA is involved with the design and the construction of the Dune field cage, and I think if there are any students who are interested with this study, then they can contact to the Professor Dr. J.U. This is an extremely important job for the successful construction of the near detector. And anyway, if we say and an energetic charged particle comes into the detector, it will ionize the argon atoms near the passage of it. And then since the whole detector is under the influence of the electric field, those ionized electrons will be drifted toward the anode plane. And by looking at the anode plane, we can obtain the X and Y two-dimensional information. And from the drift time of electrons, and more specifically, the time difference between the arrival times of the positive ions and the drifted electrons will provide us the Z coordinate information. As a result of it, we obtain full three-dimensional information of the particle track. So, therefore, the scattered electron by the dark matter will ionize the nearby atoms. And since the dark matter is almost invisible, we will see an isolated electromagnetic showers, and which is suddenly appeared inside the detector without any related pre-signature before this. And this is the most important signal feature, I think. And however, the neutrinos give us a very similar event topology by the neutral current interaction. Similar to the dark matter, neutrinos are almost invisible before they interact with the detector. Therefore, they work as a backgrounds for us. So our basic strategy is simple. Since the dark matter must have some mass of itself, those electrons scattered by dark matter will have some specific E theta kinematics, where the theta is a scattering angle of the electrons. And if we find any exotic behavior of data sample on these E theta variables, this can be interpreted as an evidence of the dark matter. So right now, I am developing a software simulating the interaction of the dark matter and the liquid argon detector. So today, we discussed what is the dark matter, and I presented about the AMS experiment. And the AMS result shows us the rising positron fraction, which can be thought as a smoking gun of the WIMP dark matter. However, there are many alternative theories that can explain such behavior of positron fraction, and therefore the AMS collaboration is keep collecting their data to obtain results in a higher energy region. Also, we need some complementary results from direct measurement to be 100% sure about the dark matter discovery. However, unfortunately, many excellent direct measurement experiments tried to find such WIMP candidates, but we don't have any positive news from now. In this situation, the right dark matter is a kind of new approach, and it is vitalizing this field again with new ideas and new opportunities. And this model introduced together with the polar interaction, and this type of study can be excellently carried by the neutrino experiment like Dune, where it utilizes high-intensity proton beam and with elaborated TPC technology. And as a postdoc member of UTA, I'm working for this subject, and right now I'm developing a software to simulate the interaction between dark matter and liquid argon. And that's all. I'm ready to take your question. Thank you for your attention.